Good afternoon, everyone. So you're here. Thanks for joining us. We're here to talk about storage for AI. I'm Swapna Yasarapu. I'm principal with Azure Storage at Microsoft. And
I'm Shashidhar Joshi, principal at Microsoft Storage.
so we'll kick it off. There we go. That's working. All right. So first, we wanted to talk to you about a little bit about how we view the life cycle of the AI workloads as it pertains to storage, and then round it up with what we see as some of the challenges and opportunities with the onset of AI for storage, especially around media, and some of our thoughts on where we would like to see us going forward. So to kick this off, right, from a life cycle perspective, we think of the AI model in these 5 stages, right? The first is about ingesting and curation of the data. So that's the raw data ingest, collect the data, prepare the data. And over here, of course, there's a role for both manipulating the data through compute and, of course, putting the data and storing it for future use. Now, of course, this drives both data growth as well as requires workload performance to make that happen. Then once the data is curated, then what we call is data tokenization. Sometimes we also refer to it as vectorization of data, where we are translating the raw data into model parameters that could be used later on in time for both training and, of course, later on for inferencing. Now, after the data is tokenized, it's in a more structured format, and that's where it goes through a coarse grain as well as a fine grain modeling. So we model or pre-train the model, and this is where we do the preliminary learning of the model. There's training ongoing over here. There's also checkpointing of the data that happens during this process. It has both computational as well as storage elements to it, where we are actually manipulating the data, learning from it, and then checkpointing it. And after that, there's also more targeted modeling and learning and training and checkpointing that happens with this data. Finally, that gets stored, and then it is used for inferencing, right, to figure out how to use these models for answering the various service questions. So, oh, thanks, Shashi. Yes, the fancy clicker would be helpful. Yep. So kind of turning this into how this flows through the various elements in the in our architectural view of the world is the ingest, of course, is the first step, as we discussed. And this is where you're actually manipulating the data and ultimately ingesting it into it. We put it on our blob storage service, which is mostly supported by hard disk drive media. This is where the data comes in, gets put in, and then we pull out this data and it goes through the vectorization or the tokenization that we discussed previously. Once that happens and the data is put into the blob store, then it goes through the training process, where now the data is pulled out of the HDD tiers and is either used through a local storage or local memory for training purposes on the GPUs. And of course, during this process, there is checkpointing that's happening. The checkpoints, depending on the version or the end of the checkpoints, mostly is sitting in our blob store again. But of course, the most recent data can also be hosted on our SSD tiers. Sometimes we call that the premium service, as we put it. And post checkpointing is when we store the results, which is then used for inferencing purposes. So what does that mean? How do we use, what does that mean in terms of the storage demands, in terms of performance and capacity? So ingest, of course, this is all about acquisition of data. And the data is in different forms. It can be raw data. It could be structured. It could be unstructured. It could be text. It could be videos. So at the system level, the media sees different types of workloads. It could be IOPS, could be throughputs. There is an element of latency over here. But generally, this is where the workload is a more varied version of the workload. Now, the next state is the curation of the data, as we discussed. And over here, the data is getting more vectorized or structured. there is a footprint reduction because we're taking all the raw data and turning into model parameters, and are stored in large block data sets. So what does that mean in terms of the system level workload requirements? Generally driven by throughput, a lot of reading happening at this point in time. And then there is some element of throughput sensitivity and of course latency sensitivity. And finally, it's the training and the checkpoint where the model parameters and the GPU scale will dictate what the ultimate requirement of the throughput levels are. But generally, these are high read, high write throughput workloads that depend on how much the GPUs are scaled. So we are looking at both system level throughput in terms of reads and writes, especially for the first fetch. There is an element to the read latency that comes in that needs to be addressed. So this is kind of how we see it at a life cycle level. And next, we'll talk about how this scales and what are the implications of that.
So this is a pictorial representation of how you would envision any training model being run on the hardware that we have. So the left side shows a simple monolithic AI hardware system. You can also think about as a rack scale based system, whereas the right side is really, our cloud scale system that goes across many GPUs at the same time. So whenever we have a training model that is being trained, and when it goes to the checkpoint model, if it needs all those parameters to be ingested all at once, each GPU is asking for the same level of data, amount of data, all at the same time. And so it accesses the blob storage, and that's where the underlying media gets stressed in the sense of we need good throughput from the underlying media to be able to service all the GPUs with the data that they're demanding. And so that turns out into the checkpoint frequency. Each customer is different, each workload is different, and so the frequency of those checkpoints varies. How many checkpoints get saved varies. Typically, we save the most recent checkpoint on the SSD layer because it's fast access, low latency. But if there's a need for accessing checkpoints beyond the most recent one, it needs to be accessed to the HDD storage tier. So scaling of GPUs is very, very important when we talk about the performance aspects. So there's many questions about, okay, what is AI data? Is it any different from what we store today, or is it really the same what we do today? So the genesis or the basis of how the data gets created, the raw data, is still the same. There's no difference between AI or non-AI data as such. How it gets used is what manifests itself into data that is just AI-centric. So here's a very simple schematic way, again, to look at things. So on the top, you will see AI data versus on the bottom, you will see non-AI data. It typically goes through the same process, which is you ingest the data, you curate it, there's some management associated with it, and then we ultimately store it into our hot, cool, cold storage layers. However, for the AI data, within the AI model lifecycle that we just talked about, if you have many checkpoints, if the model size is big, all of those things translate into more data to be stored, which is a function of AI, let's say, workloads. So when we look at performance attributes at a holistic level, there's obviously the software stack that is continuously being optimized to scale out as much as we can based on how many ever GPUs we use at the same time. Then one level below is the network. So once we have solved the software aspect of it, we have to make sure that there are no network bottlenecks in our hardware system. Then one click down is the server, which typically goes along with its compute, cache, NIC, so on and so forth. Again, those things scale accordingly with our requirements, and we can do that on the fly. So that's taken care of. And then down below is storage, where we have the aggregation of the storage in the fan-out architecture, and then accessing to the device itself. So our goal or our wish is that the media becomes the bottleneck, meaning we have solved for every other thing in the ecosystem, and then media is where we need more and more performance from. So if we look at all the workloads that we see today, currently we do see many workloads being satisfied using our HDD-based blob storage. However, we do see quite a few customer requests or workload characteristics that are demanding higher throughput in the sense of megabytes per second per terabyte. And that scales to the order of about 8 to 10x from where we are today. Now again, this performance can be solved. Think about the previous slide using all of those combinations together. So it's media, performance, it's network bottleneck solving for them, software stack, so on and so forth. And then on the very right side, you see the high watermark where there are workloads that are even more demanding than that. And this comes down to economics. So HDD-based tier can get better and better in terms of its performance, and that's where it can go to the middle in trying to scale to about 8 to 10x from where it is today. But at the same time, for SSDs, there's opportunity from an economic standpoint to get down to about 8 to 10x performance threshold in a more economic way.
Thank you, Sashi. So what does this all mean to us? So we wanted to bring in a few of our thoughts in terms of the call to action. And as we get into it, one thing we did want to acknowledge is last year we had talked about what is the call to action in terms of driving capacity density and scaling density. And the industry has responded to it, and our solutions being brought to the to the forefront to address the capacity density across both the HDD as well as the SSD flash. So that's been very great to see. And that is consistent here. So I just wanted to make a call out to the fact that, yeah, we call it out, but we are also seeing the industry respond to it. So from an HDD perspective, right, scaling throughput density with capacity density, power efficiently, right? So power becomes a very important metric in the overall grand scheme of things as we are driving to this new workload model. And that's the call to action that we need to continue to work on that, on those two metrics from an HDD perspective. And then for SSDs and flash, certainly the density scaling or capacity per device is improving, and that's a very good start in this space. And then the work that we need to do to ensure that we are also driving the TCO improvements that can deliver both on a dollar per terabyte basis while we are right-sizing the throughput density and power requirements for this space. So those are kind of the two big calls to action as we see it for storage in the world of AI in this new era. So with that, we'll take a pause and we answer questions, Lee, Ross?
Yes.
Okay.
Are there people with questions? Yeah, sure. If there are questions, there's a mic here, there's a mic there, and we can take a few questions.
So where does power come into your calculation? You had megabytes per second per terabyte. Is there a per watts?
Yes, so there's two aspects to it. There is power in terms of total capacity or gigabytes over a watt per watt basis, which also then drives the megabyte per second per terabyte per watt efficiency. But think of power as we have X amount of power, and the more we can pack into that power to deliver to the storage, there is efficiencies there.
So you mentioned that the HDDs could do 8 to 10x better. Is that you're thinking the device could do better, or maybe your stack?
So it's at a system level, but that does include improvements from the stack, from a transfer size perspective, so how we shape the IOs, It also takes into account the best HDDs that are available in the market today, or perceived to be available in the future on the roadmaps based on what we see.
Great information, but I have a question. So we talked about SSD, talked about HDD. What about distributed storage? Do you use any distributed storage at all for AI workloads? You mentioned blob, but can you talk more about distributed storage, if it's being used at all for AI?
Could you repeat the question if you don't mind?
So you talked about SSD, you talked about HDD.
If you can get closer, if you can get closer to the mic.
Sorry. Yeah. So you talked about SSD, you talked about HDD storage. Can you talk about distributed storage, if it's being used for AI workloads at all?
Distributed storage.
Yes.
Got it. Yes. So in our version of the world, we are a distributed storage system already. And I think that's where we talked about the scaling, right? Because as we are scaling out to be able to address the requirements from the training and the checkpointing workloads that come down to us through the GPUs, it is a question that needs to be addressed in the context of distributed, scaled out storage to provide the capabilities of both storing as well as servicing the data.
Maybe to kind of expand on that question, you showed the media tiers as being a flash tier and a hard drive tier, but what kind of limitations do you see in terms of the network getting from a network attached flash media tier to the compute servers when you're doing training workloads? Do you see the network as being a bottleneck and requiring a non-network attached flash tier? And I also had another question about checkpointing and kind of what's the high watermark in terms of checkpointing, and do you see any limitations about flash media serving the checkpoint application well?
Okay. Would you?
So I can address the checkpointing. So it's predominantly is a function of how big the model gets. The bigger the models, the larger the span they go across all the GPUs. And then that requires just more data that is checkpointed. So that's where it will stress the underlying layers of hardware that we have to go service. Your first part of the question was network. So like we showed, network is certainly one of the bottlenecks. Our effort is to try and solve it all the way down to the media. So it could be the top of the rack switch. It could be the NIC that sits in the server. It could be even our network switch coming in from outside into the data center. So those are all valid bottlenecks, but we have solved those and in the process of solving the ones that are still maybe to be solved. If you want to.
No, I think you hit it. Great. Thank you, everyone.
Thank you.